Hello, welcome to 3.3. We're on the page 1 of it, the notes as well. And we've got this change of base formula. And to be perfectly honest, this change of base is really a bit antiquated with the technology of graphing calculators. However, we're going to go ahead and go through it. Let's say, for instance, I wanted log base 3 of 17. And we know now that's a great way to say it, terrible way to think of it. This is the exponent that turns 3 into 17. Well, 3 to the second is 9, 3 to the third is 27, so it's somewhere between 2 and 3 is the exponent. So what this says right here is the change of base formula says if I've got log base a of x, I can make log base, choose a whole new value b and put for the base, and put the x up top, the a in the bottom as the arguments. In other words, this could be written as plain old log 17 on log 3. Reminder, this should appear in your notes. It's part of your assignment. So let's take a look at that. And if I do that one, I get log 17 divided by log of, and this is of course base 10, base 3, and I get 2.5789, etc. Somewhere between 2 and 3 as we expected. I also could write that as ln 17 on ln 3 using log base e. So let's see, ln 17 divided by ln 3. And we get the same thing. So there you've got it. We've got our choices, and typically in the past we would either go to log base 10 or ln if our calculator supported log base e, ln, and that's how we would find log base 3 of 17. But as we know, we can alpha window and go log base 3 of 17, and we see, you know what? It doesn't matter. I could choose whatever base we wanted. I mean, arbitrarily, I could say this is log base 94 of 17 on log base 94 of 3. I can choose whatever value I want for b. So there you go. Okay, I'm not going to give a full proof of these properties down here, but when we have log of a product, we can turn that into log of the sums. And it's the same for ln. You know, this is log whatever base we want. Well, ln is log, hey, I want base e. But this has a whole lot to do with this rule from algebra. X to the second times x to the third. Now, there's no reason we should miss this other than we memorized and didn't understand the rule. But this really means x times x times x times x times x, or x to the fifth. So there's rule 1. So what happens when I have a product with exponents, we end up adding the exponents. That's really what's happening here. We're dealing in exponents here. We have a product in this exponent, and we end up adding the exponent. Now, that leaves some gray area, but that might help you remember. So how about when we have x to the fifth on x to the third, we know that's x, 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 x over x, 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 cancel, cancel, and we get x squared. So we take 5 minus 3, and we just get x squared. Well, when we have a quotient with exponents, we subtract the exponents, and that's what we're doing here. And then rule 3, if I have x squared to the third, that means xx, xxx, xx. I have 3 groups of 2 x's, and that's the way I like to say it, because that shows understanding. People who miss this by going x to the 6th are people who have memorized that. And you might have been taught to memorize it. Let's break free of that memorization. It causes problems down the road. A pair of x's, another 3x's, we're multiplying 5x's together, x to the fifth. 5x's on 3x's, we cancel them. But here, 3 groups of 2x's. So I'll see people that will put down x to the fifth for this, or even x to the eighth. They'll take the 2 to the third, x to the eighth. But it's not. It's 3 groups of 2x's, 6x's. So when we have an exponent log with an exponent with an exponent, what do? We multiply the exponents. N's an exponent, and log base a of u is an exponent. Okay, so those are our 3 rules that allow us to kind of either, working this way, smash together logarithms, or separate logarithms into more simple arguments. And that's what this section is about. So let's go ahead and get started. This starts out with just, we're supposed to rewrite logarithm as a ratio of common logarithms and natural logarithms. And that's what we're doing, what we did right back here in this first set change of base formula. So here's how easy this is. This is just log base x on log base 3. Isn't it nice? This one goes on top, the lower one goes on the bottom. And ln x ln 3. Log base x on log base 1 log 1/4, excuse me, that's natural log, or ln x on ln 1/4, etc. Log 4/5 on log base 10, well, I'm doing it again, of a, or ln 4/5 on ln a. Log x on log 7.1, or ln x on ln 7.1. And believe me, there may be times when that becomes useful, but for the most part, we would just enter this in our, we'd have access to enter calculator of a base 7.1, a base 3, a base 1/4. It's not the problem that it used to be for us. So technology, another hug your calculator moment. Okay, so I want to rewrite this in terms of ln of 4 and ln of 5, which means I need to get that 500 factored down, broken down into powers of 4 and powers of 5. So I'm going to go old school factor tree here. We get 5 times 100. I like the 5. We want 5s, we want 4s. So I get 4 and 25. I like the 4. 5 and 5. So this is ln 5 to the third times 4. Why didn't I break the 4 down? I don't want 2s. I want 4s. So this is a 3 right here. And now, back to our properties from the previous page. Here I've got a product. That says if I've got a product inside logarithms, I can break that product into sums, into a sum. So this is ln 5 to the third plus ln 4 by property 1. Now property 3 says if I have a power in there, I can bring that out in front. Now notice I couldn't bring that 3 out in front here because it's not the whole argument cubed. But now it is. The whole argument is 5 cubed. So I get 3 ln 5 plus ln 4, and that is what we're looking for. This is equivalent to this, and you can check it on your calculator if you'd like, but now everything's in terms of 4s and 5s. And where I really like that as far as quizzing and testing is what we're going to be taking a look at 26 and 28. But let's go through 24. Sneaky here. This is ln, I like the 5, but I'm going to write this. 2 is the square root of 4, but the square root of 4 can be written as 4 to the 1/2 power. Now, by rule 2, if I have a quotient, I can split that out into log of the numerator minus log of the denominator. So this becomes ln 5 minus ln 4 to the 1/2. And now by rule 3, I want to get that exponent out of there. If I have log with an exponent, the exponent can come out in front. So I end up ln 5 minus 1/2 ln 4. Okay? So here is the deal. You will definitely have problems like this, and perhaps we could even figure out, we could work through this and figure out what the value of b is here. We're not going to do it that way. Approximate the logarithm using properties of logarithms given the values. Okay, we know what log base b, whatever it is, of 2, we know what it is. And we know what log base b of 3 is, and we know what log base b of 5 is. So I want to write 30 in terms of 2's and 3's and 5's, just like we were doing up here. So we'll box that one too. So 30 factors into 3 times 10, or 3 times 2 times 5. So if I treat this as log base b of 2 times 3 times 5, property 1, if you look at it, allows me to write that as log base b of 2 plus log base b of 3 plus log base b of 5, or 0.3562 plus 0.5646 plus 0.8271, and definite calculator support for that. On 0.35, not that we couldn't do it, plus 0.5646, is that right? Yep. Plus 0.8271, a quick double check, and we get 1.7479. And then 28, well, this is already a 3. Why don't we treat this like log base b of 3 to the 1/2, the square root, and that lets us use the power property, or number 3. I get 1/2 log base b of 3, or 1/2 times 0.5646, which is 0.2823. So that should be a fairly quick page for you. Questions if you have them. Make certain that you're taking care of yourself. You be your biggest advocate. Okay, we'll see you soon.